So in this clip, we are going to discuss what's happening on capillaries. So there is the exchange of gases and nutrients, and that is happening by filtration of fluid from the vessels to the surrounding tissue and then resorbing it back. So we will review the structure and function of capillaries, look at the forces that play a role in fluid movement from capillaries to tissue and back, and see how the capillaries are related to the lymphatic system. And then we will discuss some clinical problems that may occur because of issues on capillaries. At the end, we are going to calculate the balance of hydrostatic and oncotic pressure on the capillaries so that you can actually practically apply your knowledge. So capillaries are very thin-walled vessels. They don't have any smooth muscle. They have the only one layer of endothelial cells in their wall. And in this picture, you see 200 magnification of a capillary where red blood cells are at the moment passing, right? So capillaries are very tiny vessels, and in systemic circulation, meaning the circulation that brings the oxygenated blood from the heart to tissues, it is about delivery of oxygen and nutrients to the cells around the body. And then in pulmonary capillaries, the blood is oxygenated and the catabolites, carbon dioxide, is removed from the circulation as we exhale it. So different processes are happening on systemic and pulmonary capillaries, but it is all about movement of fluids and the balance of the forces. So Starling was a physiologist at the beginning of 20th century in England, and he described the forces that are happening on capillaries. So there are mainly two kinds: hydrostatic forces and oncotic pressure. So hydrostatic pressure is the pressure of the blood inside the vessel on the wall of the capillary. But then we have also hydrostatic pressure of the tissue around the capillary, right? So hence they calculate net hydrostatic pressure, that in this case is mainly the pressure in the vessel and not much pressure around, which is considered zero. So we have net hydrostatic pressure, 35 millimeter mercury. We also have something called oncotic pressure, and this is the force or the ability of proteins to, especially albumins, to hold on water. So in the plasma, we have proteins, and as they hold the water, they express the oncotic pressure. So they have the oncotic force, and inside the vessel is 26, and then we have some proteins also around the vessel. So here they put it as a small force of 1 millimeter mercury, and now we have a force that pushes the blood or the fluid plasma out of the vessel, and force that holds it in. So net filtration pressure is 35 millimeter mercury minus 25 millimeter mercury, which gives a force of 10 millimeter. So at the arterial end of the capillary, the fluid is going out because the pressure is having the direction that goes outwardly. As the fluid is being filtered out of the arterial end of capillary, this hydrostatic pressure of the blood on the wall of capillary is decreasing. There is now less fluid, right? So we have now, for example, 17 millimeter mercury of net hydrostatic pressure, but the amount of proteins between the arterial and venous end didn't change. So the oncotic pressure remained at the venous end of capillary, same as in the arterial end of capillary. So the force is changed, and now we have 17 minus 25. So this resulted in the force of negative 8 millimeter net filtration pressure. In other words, absorption of the fluid. So here we have filtration, and then as the forces changes, we have absorption. And this is an ongoing process that is happening around the cells, around the whole body, and it's happening all the time. Now, you may notice that we have here a filtration of 10 millimeter mercury, and here the absorption was 8 millimeter mercury. So obviously not all the fluid gets reabsorbed. So you can wonder how this is being handled, and the body actually came up with some very interesting design where the fluid around the capillary network is picked by lymphatic vessels. So lymphatic vessels start in the tissue and takes in the small portion that is not being absorbed and runs it through lymphatic vessels that are actually interrupted by lymphatic nodes. And in that way, there is a constant surveillance of fluid by a lymphatic system. Now, the fluid doesn't disappear. It actually accumulates in the big lymphatic vessels, like lymphatic duct and thoracic duct, and those then bring the fluid into the large veins. So as a result, we have a constant filtration of fluid and absorption. So we are bringing nutrients and bringing oxygen and removing CO2. And the small amount of fluid also is checked whether there is any infectious pathogen that immune response needs to respond to. So what could go wrong? So, for example, if we don't have enough albumin, we will not have sufficient force of proteins to hold the water in. And as a result, more will go outwardly and edema occurs. So the situations where we have a smaller amount of albumin are happening in situations where either liver is not able to make it or kidney lose a lot of protein. So liver and kidney diseases are associated with edemas because of low oncotic pressure. Then we have here a possibility of hydrostatic pressure, and the hydrostatic pressure at venous end is, for example, happening during congestive heart failure, where pulmonary edema develops because the hydrostatic pressure remains high here as the blood cannot move away from the venous end. It's accumulated, and if this remains high, then there will be lesser resorption potential. And the other problem could be that this small discrepancy, the small volume that is being run through the lymphatic system may not be able to be drained. So if there is some occlusion of lymphatic system, as it is in this woman where the parasites are occluding the lymphatic nodes, they will not be able to remove the fluid, and you see that after a long time, the edema can be actually very significant. So now we have an example of the forces that can be changed. So if we are at arterial end and we have hydrostatic pressure, net hydrostatic pressure, 38 millimeter mercury, and oncotic pressure, 25 millimeter mercury. So what is the net filtration pressure at the arterial end? So hydrostatic pressure is an outwardly force and the oncotic pressure inwardly. So 38 minus 25 milligram mercury gives you 13 millimeter mercury of filtration, net filtration pressure. At the venous end, you may have lower hydrostatic pressure, so 15 millimeter mercury, and oncotic pressure remains same as it was in the first case, and so it's 25. So now 15 minus 25 gives you negative 10, and so the net filtration is negative 10, and therefore it is the absorption of the fluid. But not all fluid was absorbed. Here we had the difference 13, here net filtration pressure 13, here we have net filtration pressure 10. So where does the non-absorbed fluid go? The fluid corresponding to 3 millimeter mercury pressure is now traveling through lymphatic vessels, lymphatic nodes, until they are emptied into large veins.